I welcome you all in this session. This session has got 4 speakers. I'll just read out the name, but I'll give the intro about the speakers before their presentations. Actually, they are Professor Luis Ambrosio, Ana Casa Jacqueline, Professor Piero Demetrio Florsi, Flavio. First, we are planning like that. We have 15 minutes. I request for the speaker, distinguished speaker. We have got around 50 minutes, but we are 60 minutes for the session. We'll plan like 15 minutes each, then followed by 2-3 minute discussion, 5 minutes for closing. We have planned like that. First, I'd like to introduce my first speaker. Is a Professor Luis Ambrosio. He's a professor of statistics, econometrics, operational research in the Polytechnic University of Madrid, Spain. He has contributed significantly as a FAO consultant in agriculture sampling design. He has been a leader of more than 25 important projects and has published more than 25 research papers. Currently, is contributing in so many important projects funded by different UN organizations. With this, first I'll request my first speaker, Professor Ambrosio, to please take the, I think your slide is here already.
Okay, thank you. Okay, thank you, Chair. I will make my presentation in the framework of this last project. It's a project that is financed by the European Spatial Agency. You know, it is the equivalent to the equivalent for Europe to the NASA. And we are carrying out the project in collaboration with the FAO and the World Bank. The objective of the project is improving the use of remote sensing data in agricultural statistics. And that we are trying to do that from the beginning. That means from the sampling design to the that means for the estimation at the usual level. I mean at the national level, the regional level, the local or small area estimation level, and also at the global level, because FAO and the World Bank are interested in having early forecast of crops, acreage, and yields to prevent food security disasters. Well, let's begin with the sampling, the application of remote sensing, particularly to sampling designs. You know that to identify a cost-efficient sampling strategy, it is required to identify a class of designs and to identify a cost function. The class of design is then searched for the design that minimize the variance for a given cost. The problem is that to identify this variance, we need to specify a model because the variance is in practice is unknown. So we must specify a design model in order to calculate and to estimate the anticipated variance under this model. The class of sampling design, or sample design that we are considering is sampling in area sampling in particular. Here you have a classical area frame. You know, the small square are the sampling unit, call it segment, and a first sampling scheme will be sample random sampling. That means we could to select a sample of segments with equal probabilities. A second sampling strategy that we will consider is stratified selection. You know, this sampling strategy consists in dividing the frame, the area frame, into small areas called tesalas from the, from the geography, and then we can select a small sample of segments in each tesala. And the third sampling design that we are considering is a systematic sample. This sampling scheme is applied by selecting a random, a random star, in systematic sample. We select a random one segment from a tesala, and then we include into the sample the whole segment that occupy in the same position in each tesala that the one selected at the beginning. Regarding the cost of function, we consider, as usual, an additive cost function with two main components, a fixed cost and a variable cost. The main fixed cost is the frame building cost, and the main variable costs are the travel costs of interviewers and supervisors and the cost of the interviews. This includes the cost of location the sampling unit. For instance, for simple random sample, we consider the cost function as usual with these three terms. About the model for the design, we consider a random field. In this random field, we assume that the means and the variance are constant within a given stratum, and the sampling unit are not independent, but they are correlate. And to model the spatial correlation, we consider, as usual, variogram or correlogram, where the variance is a function of the distance, the Euclidean distance between the sampling units. Here you have one usual model that is the spherical model of the variogram. Here you have an example of empirical variogram. This is a variogram corresponding to the herbaceous, non-irrigated herbaceous in a region from Spain, is Castilla y León. You can see that it's really nice because it fits very well to theoretical model of this kind of variogram. We compute this variogram 10 years ago, and well, it was really hard because you know that each one of this function, you need that at least 100 of couple of sampling points. you know. Now we are planning in this project that this kind of estimated variogram can be computed in a way a lot more cheaper, because we have a lot of data, and we have also the application developed. This is the big data from a world that we can use to arrive to estimate the spatial correlation. And this is one of our objectives. Using this correlation variogram, this variogram or this correlogram, we can compute the anticipated variance. For instance, for the replicate systematic sampling, here you have the anticipated variance. You can see that is also hard to do. It's not an easy problem, but in this case, it's a problem that was already solved by, particularly by DAS. I think that here, just in India, because I don't know, Chair, if DAS is from your department, was from your department some years ago, 70 years ago. You know, you do remember that. I think that is, but in any case, this computation of the expected variance is public, is available. You can see that the correlation, that the expected variance depends on the correlation between couples of sampling units in the population. This is, I don't know if it could, is the first term of this expression. It depends also on the average correlation between sampling units of the same systematic same systematic sample, and finally it depends of the average correlation between population units within a sampling unit. Sampling unit that, as you know, is called a segment. Using the variogram, we can compute the relative efficiency between the three sampling strategies that we have considered. Here, for example, you have the efficiency between systematic and random sample. This relative efficiency depends on the correlation, on the spatial correlation. That means that if there is no correlation, all the sampling strategies have the same expected variance. That means that they are equally efficient. I want to say that is very important. It is the spatial correlation in this in spatial sampling. It is the spatial correlation that makes the difference. Then we can formulate the optimization problem. As you can see, for instance, for random sample, the problem is to find the optimal value of the sampling variables. Of the sampling variables are here. The size of the segment is N0. the size of the sample, the number of the segment to be included in the sample, and in addition of the size of the population and of the variance, and the correlation between couples of population units within a segment. You have also there the cost function, and the problem is to find the optimal value of the number of sampling of population unit to include in a sampling unit, in a segment, and the number of the segment to include in the sample. In the same way, you have for the other strategy, the stratified tessellation. The problem is to find the optimal solution of the segment size and the size of the tessella, and also the size of the sample, the size of the sample to be selected in each tessella. And the cost function is different from the cost function of the other strategy. And finally, we have for the systematic sampling strategy, the problem is to find the solution also of the segment size. This time is the size of a systematic sample and the number of systematic samples to be selected. Okay, I finish. Here we have the solution for a case study. The case study is the Castilla y León in Spain. And you can see there that, as expected from the theoretical point of view, the optimal size of the segment is a segment with only one population unit, you know. You can see how, as the segment size increase, the expected variance increase also, and this for a given cost. That means that the optimum is only one population unit by segment. Here is the optimal solution for the second strategy, it's a stratified tessellation, and you can see here also that the optimal is 2 segments by tessella, and you can see how the number of tessella in the optimum should be as big as possible. You can see also how the expected variance increase if the number of tessellas decrease. And finally, we have here the systematic sampling, and here the solution doesn't change because the lower bound in the optimum is over the lower bound. These empirical results are in agreement with the result obtained theoretically by Cochrane at the beginning, by Das, I say, and also by Kenuil and Bellhaus. And this is because our variogram, our empirical variogram, fit very well the theoretical model uses in this by this author. But we think that our approach can be used whatever the empirical variogram is. Finally, we can see here the result of a sensitivity analysis that we have carried out. And you can see that if, for example, the cost is increased 15%, then the solution is that the sample size is lower, but the relative efficiency between the segment size is the same. The same is also if the interviewing cost increase also, and in this case the sample size also decrease, and the expected variance increase, but the relative efficiency is the same in both cases, and the same for the budget. One more minute to remember you that, in fact, when the sampling design, yeah, it's okay. The sampling design generally is multi-purpose. And in this case, is evident that the optimal design for a purpose is not the same for other purpose. And then we suggest to assign a relative value of importance, a weight to each purpose, and the reformulated optimization problem but using a function that is a weighting average of the different purposes. The solution can be obtained in the same way in this case. For concluding, we remember that for finding the optimum segment size and the optimum sample size, we propose identifying the spatial correlation function empirically using this time satellite image, and then anticipating the sampling variance, specifying a cost function that is also very, very important. To put the focus in the cost function is very important, and then minimizing the anticipated variance subject to the available cost, or minimizing the cost for a given anticipated variance. We have proof that the proposed approach is useful for choosing the cost-efficient sampling strategy and for optimizing the sampling design in practice. As I say, whatever the empirical correlation function is. And we have analyzed also the sensitivity, and we have found that this approach is robust with respect to the change of the parameters considered. That's all. Thank you so much.
Oh, yes, please. Do you have got a set? No, it's fine. You, Anna. Yes. Have you got it's already here. Yes, already here. Have you got anything to introduce? Because I could not get
okay.
To give the introduction about you.
Yeah, okay.
What you are somewhere here?
Senior statistician, yes.
Okay, senior. Okay, thank you. I'll just please have a seat. Thank you, Professor Ambrosio. We are running a bit late because session started late, but we have to finish in time, keeping that in view. I'll just give a brief about the second speaker. She has just joined, actually, right now. She's Anna-Kaisa Jackman. She's a senior statistician from LUIC, Natural Resource Institute, Finland. I think I'll not take much time. Rather, I'll allow a speaker. Are you okay? Otherwise, I can interchange the speaker. If you want time to settle down, I can request the... Because we are, anyway, we are mixed up with the time because we started late. You okay? Otherwise, okay, yeah. Then with this, I request you, Dr. Anna, to please take over the mic and just start your presentation. Slide is here. Okay. Yeah, please. And you have got around 12 to 14 minutes. When you say around 2 minutes, I'll indicate you.
Okay, thank you. Hello, everybody, and nice to be here. We were in the wrong place. I'm sorry, but now we are here. I'm senior statistician Anna-Kaisa Jaakkonen from Luke, Natural Research Institute, Finland, and I'm expert in horticulture production, not in statistics. My colleague Mika Kuoppaho is there. Very difficult statistical questions are maybe better for him. And our topic is improving efficiency of the sample design in Finnish horticultural survey. At first, what is Finland and horticulture and agriculture? We have horticulture really in very north in Europe, near at same level as Alaska is. It's not so normal to have horticulture and greenhouse production in so north, but in Finland people like to eat Finnish vegetables and flowers. And another thing is this standard output as classification instrument, how to make better samples in a very practical way. And it's part of this our cut-off sampling system. Maybe this better. Our company, Natural Research Institute Finland, is research expert and statistical organization. Not only statistics, but also research all around the world. And our customers, we are trying to get customers by solving local and global challenges also. Forest is very important in Finland, but also agriculture and aquaculture. And here you can see where we have international development projects. We address these global challenges and provide sustainable and innovative solutions for demanding problems connecting, for example, food safety and sustainable agriculture and forestry. And there is one connection between Finland and India, and it's curry and biryani, because Finland is currently the world's largest producer of caraway seeds, one part of curry. Not so typical. Horticulture and agriculture in Finland, it's very small scale, but we have the most important part of our agriculture is dairy products. But we have also vegetables and flowers. Agriculture is in Finland family business, not so big one, but this is very typical Finnish couple of farmers. We have lakes and forests, and also we have a little bit strawberries. Berries and strawberries are the most important berries in Finland, and we have also outdoor vegetables, carrots, onions, cabbage, so on. And production in greenhouse is very important for us because we have very cold winter time. As you can see, we have snow, dark, we need lights. And nowadays we have cultivation under light about 25% of all greenhouse area. And cultivation under light is very expensive, so we have now LED lights. They are not so expensive. They are using less electricity. The focus in horticulture statistics in Finland is towards the large production that enters to the market and not in small kitchen farms and less in social aspects. In Finland, we not really have kitchen gardens or only hobby gardens, I can say. And our main target is to evaluate economical value and amounts of horticultural products to the market. It's money it talks. But there is also other data needs, such as estimates for food security, and we can utilize the crop area from agricultural register with full coverage of utilized agricultural area. And this is not very typical in world. We have so much information of our farmers and production and areas. It makes much more easier to make statistics when we have very good backgrounds. Our horticultural survey, it's mixed mode in advanced letter and web survey and telephone interviews. Web response rate is quite high, 55% of all respondents. And total response rate is close in 98 of horticultural farms. Finnish farmers are quite good to answer our questions. It's very important for us. And the coverage is almost 100% of the land of horticultural production. And for missing answers, we are using donor imputation of the nearest neighborhood. And our need target is to reduce response burden of enterprises and reduce survey cost without sacrificing the accuracy and quality of the survey information. And we are using standard output in classification. Standard output is useful and easy classification variable for different types of horticultural production, better than, for example, areas. And standard output is abstract computational variable, and it puts all production in same line, euro line, or money line. Standard output is the average economical yield for farm producers per hectare or per production animal, excluding agricultural benefits for production. And at present, the threshold is little over $2,000 or 2,000 euros in the frame population in statistical register of farms and horticultural enterprises. And it's based ICAS, Integrated Administration and Control System in European Union. As you can see in examples, vegetables are more expensive than, for example, oats or potatoes. And animals have their own numbers. And this is a very good way to calculate what is the standard output per one farm. We can put them online for smallest to biggest one. And how we are using standard output in optimizing survey cost and quality. First, you know, we have survey cost. Fixed cost is designing and testing questionnaire, designing web questionnaire, building databases, building dissemination channels of statistics, and mailing advanced letters, normal costs. And varying costs are reminders of those not responding through web. And second, advanced letters for those to be interviewed in telephone, and telephone interview fees per interview, and all contact attempts done by interviews. It costs quite much money. And we are trying to define the optimal cutoff. As response rate in web increase, these varying costs are being minimized. And maybe it's a bit better to look at this picture. Here you can see our system. All farms are left in axis X. And we put in order, smallest are down and the biggest one is out. And of course, after that we are using this cut-off level. Cut-off level is, we are minimizing standard output from, normally standard output was 2,000 euros, now it's 10,000 euros. When cut-off level going down, cost goes down, but quality is not going down, because the biggest farms are in our questionnaire, our survey, and the smallest one are imputed. And this is very important for us to get good enough quality, but not so much costs. And we have theoretical background of our work, but this is only copy for text. But this is quite practical way to make statistics. In practice, you can see here, if we have for the horticultural farmers about 3,500, after cutting off some system, we have in survey only 2,700 farms. And this way we can improve efficiency by 800 units and saving money and reduction of response burden by 23%. And our practical thing is good enough is the new best to get statistics with not so cost, but quality is good. Thank you. In time.
Thank you, Anna. I'm not taking any question right now for the speaker. I'll take it end of the presentations once, if time permits. Okay. Now I'll introduce the next speaker. So Dr. Flavio Voliger. He's a very well-known figure. I think many audience already know you, Flavio. I'll give a brief introduction. He's a senior statistician in Statistics Division of Rome, Italy. He has led the global strategy program. I think by that time, actually, many people knows Flavio very well. Before that, he was in a very renowned institution, IBGE. That is a Brazilian Institute of Geography and Statistics. He has worked as a coordinator for agriculture. I'll not take much time. Actually, I'll rather give more time to a speaker. I request Flavio to please take over the mic and just start your presentation. Oh, again, you have 12 minutes.
Well, this paper is about non-overlap sampling for agricultural statistics. It is about how to apply this methodology on agricultural surveys. The paper is from me, Adriana Diniz from IBG, and Silva Miciroli, my colleague on the ESS FAO. The original idea came from Andrea, because she worked on new modality of census for population census, but the idea is to apply the same kind of technique in agriculture. I will skip this outline. Okay, non-overlap sampling. We should talk about, mention Leslie Kish on this topic. He produced many papers on the subject since 1981, so it's not a new idea. No? Cumulate estimates from balanced samplers collect over time. It's more or less the general idea of the non-overlapping whole sampling. There are some outstanding applications, like the population census of France nowadays is using it in the population census, the American Community Survey, and many household survey, including the household survey of Brazil using this kind of technique. But we saw this mainly on household survey. And we have no notice about the farm survey based on non-overlapping whole sample. Okay, agricultural statistics has some characteristics and that should take in account. The difference from household surveys normally, especially the labor survey or this kind of survey. A reference period normally is 12 months. We are interested on the production of the entire year, covering all the seasons, all the crops, all the activities. Many times they are interested on have information about the major crop during or the minor crop, no? In the dry season or in the wet season. There is also interest on do early estimates. So it's very common to apply survey after the planting, the post-planting surveys, but also about the final production. And detailed information is also required because different conditions across the country derive from natural characteristics of the agricultural activities. The common approach we found in many countries is a panel survey, a sample that is repeated year after year, the same sample. And the sample design normally is defined according to certain domains, maybe regions or provinces, and certain strata to more efficient estimation. And the way to get data normally is face-to-face interview. And to fill some of the requirements I just mentioned, it's very common to have post-planting and post-harvesting data collection in 2 moments, or data collection regarding the wet season and dry season. So in some cases, it's 1 visit, 2 visits, or 4 visits during the year. Okay, to talk about non-overlap sampling, we are adopting this hypothetical scenario that we have the calendar year as a reference, could be agricultural year, but it's the same. Interest on domains on national, region, and provinces. 2 seasons, dry and wet season. And we are talking about a way to, or a cost-efficient way to collect data. So we start with a common case that we have a budget to be spent, so a restriction in terms of the budget. So in our hypothetical scenario, we are talking about a budget of 1 million, and the data collection unit costs 100. So it allows a sample of 10,000 observation, 10,000 observation. And an assumption, just for explanation, we have assumption that 2,500 cases is enough for a reasonable estimate at national level, 5,000 for a regional level, and we need 10,000 for get estimation in the province level. This is just to explain the idea. Okay. We are considering 5 survey design. First, single sampling, that's the general case. And we can have a single sampling, but do just 1 visit in the year. You can do 2 visits or 4 visits, as I mentioned. In many cases, it's more than 1 visit. And the alternative is non-overlapping whole sampling, considering 2 groups or 4 groups, and you'll see this. Okay, in the single sample, first to understand this figure, this bar with green and yellow, green is the wet season, yellow is the dry season. This small square, it could be a report, but in fact it's the tablet, no? It's a data collection, so we're after the period of reference, we have the data collection, and some months later, the release data. So, in the first case is the single sampling with 1 visit. After 1 year, we go to the field and we have the annual report about national, regional, and province level, because we will have this size of 10,000 sample. But if you go for 2 visits, 1 visit for the major crop, another visit for the minor crop, or we should have the total sample of 5,000 only, because we are spending our budget with 2 visits during the year. In this case, you have advantage to have more timely data, because you can produce a bulletin about the wet season in the middle of the year, and in the end of the year, a bulletin about the dry season and the annual report. In the case of non-overlapping sampling, the application we thought is to define two groups. So we have the same total sample, 10,000, but we define two groups. You select two groups, so two samples of 5,000. So one sample, we do the collection in the middle of the year, but get information about the last 12 months. So the previous dry season, and then the wet season. And with that, we have the same results. We have this wet season bulletin, but we also can provide data on agricultural year report, considering the previous seasons in the national and regional levels. So 6 months later, you can do we do another round of data collection with a new sample, a completely new sample, the second group. And with that, we got the same results we got with the two visits approach, but with the advantage to have these other reports and advantage to have a bigger sample. So in the end, 10,000. In fact, to have 10,000 observations about the phenomena in the two semester or season, we are talking about a rolling sampling. So every 6 months, the data collection with a third group. With that, we can get information about the wet season and the dry season with the size of 10,000. And then it's possible to produce data at province level. So with the same budget, okay. In fact, do data collection in a panel is less costly that goes to a different farm every time. We have a marginal additional cost, but we have a lot of advantage we will explain later. So in any case, with that, we can improve the precision and the area of domains that we can produce data. Just to explain that, first we get 5,000, 10,000 observations for the wet, and later 10,000 for the dry season. With that, we can produce data in the province level. Another case is the single sampling with 4 visits. That is very common. Normally it's post-planting, post-harvest, and for two seasons, or for GDP purpose. Many countries have this approach. Again, a panel and 4 visits with the same sample. In this case, the size of the sample should be 2,500. So only national level estimates can be done. 2 minutes, okay. Well, the same schema can on overlapping with 4 data collection. We arrive with a more timely information and in the same level of the tail information. Well, this square, this table shows some qualitative aspects. So in the end, with the non-overlapping rolling sampling, we can get this more detailed, more frequency of results, but we have some delay in terms of the results. Just to compare one visit case, we can have all levels just some months after the end of the year. And in the case of the non-overlapping sampling, the same results can be obtained after 1 year. accumulating data of the 7 rounds. Well, this is just, we have some household survey that has a model on agriculture. We present data from the socioeconomic survey of Cambodia and the Malawi integrated household survey. This is not exactly non-overlapping approach because they don't have an independent sample for each month or balanced sample, but give us an idea that the precision we get in just with the sample of each month and the precision we get with accumulating data of the 12 months. Well, I skipped that. Oh. Okay. With non-overlapping sampling allows decreasing respondent burden, because we interview just one time each farm, one time. A compromise on recall bias, because some different moments of interview. So part of the sample, we're going in the better moment and the others later. We increase the frequency of data release. We can produce both calendar year or agricultural year's data and have a more efficient use of resources available. But the most important advantage are improving precision, because we can, with the same budget, we can increase the sample size, and we can increase the number of domains that with a higher sample size. Or it's possible to reduce the expenses if you stick with the same sample size but spread the data collection in many moments and with more cases. Well, the trade-off I already commented. This is the intention of the paper is just to open the discussion about this possibility. Many studies are required to develop the application for agricultural statistics. Some themes could be appropriate survey questionnaire in this case, because it's possible to combine the questionnaire information for early estimate or previous production in the previous period. The question of frame update, because it's a rolling sampling, we should update over time. The way to produce balanced sample, and with this a special case of the specialized and large farms. In agricultural survey, normally we have a strata of take-all cases. We go with census, because they are very different, very special cases, and it's very hard to distribute this case in a balanced way, because each group or each sample should be able to produce data for the entire population, target population. So one idea is to, with this group, goes to a panel. Also, other teams are procedures to accumulate the estimate, calculation of the variance, and the idea that comes from Leslie Kish, that the possibility to accumulate data of many years, 5 years at least, taking in consideration structural variables, and this as a possible alternative of, for census objectives. Thank you.
Thank you, Dr. Flavio. It was a nice presentation, but as you know, we have very limited time. But we have option actually. Later on, we will be getting the full papers. I'll announce that later once session is over. Now, next speaker is Dr. Pyro Demetrio Folarsi. He's Head of Central Management for Methodology and Design of Italian Institute of is on division statistical process. He has more than 30 years of experience in design and implementation of methodology, architectural aspect related to statistical survey and register. He has worked in many national and international project organization. He has got huge experience, both research and policy related. I will not take much time because we are running late. I request Dr. Fayed to please start his presentation. Thank
you. Thank you, Okum, for having invited me in this session, for having considered. This is a paper with 3 authors, with Paolo Righi and Pierre Lavalle, formerly in Statistics Canada. I will give an introduction and background. I will describe the problem, and I will describe how the problem can be performed in different informative contexts. I will conclude with some empirical results and conclusions. The problem, the introduction, often need to observe together different populations related to each other in social or economic studies. In agricultural studies, we observe the farms, and we need to observe the households related to farms. For instance, in farms, we observe the productivity of the farm. In the household, we need to observe the level of nourishment of the household or level of education. The two phenomena are related, but population to be sampled are different. This is a very general framework. We can observe herd, and the second population can be that of farms. That is a very general scheme. Page down. The integrated observation is used for studying phenomena that are correlated but belong to different statistical populations. Allows to study the relationship about all the variables of interest for the given phenomena, even if they belong to different populations, and independent observation of such population would not allow the observation of the set of all related variables of interest, or even worse, could lead to biased inference on one of the two populations. Indirect sampling provides a natural framework for the estimation of the parameters of two target populations, and units belong to a population that are selected for a given survey enable the collection of information of another population through the links on the relationships between the units of the two populations. The problem is what sampling design used for the integrated observation of different populations. Indirect sampling design is implemented. The focus of this presentation of the determination of optimal sampling sites, but when we have a multivariate, we have many variables of interest and multi-domain problem, and different domains of interest. And this presentation is a generalization of the Falorzi and paper of survey methodology 2015. Now I will give a very short sum notation thanks to the agricultural context. The first population, UA, A is the first population, is the population of farms, and UB is the second population of households, A and B. We have example A selected from the first population, and we have the inclusion probability for each unit in the first population, and we have the vector of inclusion probability. Our target parameter is the total of the Y variable, and we estimate it by the usual Horvitz-Thompson estimator. For estimating the variance, we propose the approximation by DeVille and Tillet 2005, a very powerful approximation because it allows to compute the variances using only first order inclusion probabilities, and this is the variance is the variance of transformed variable considering the residuals with a given vector of points for which the estimated the estimates are needed. But if you consider a simple stratified random design, this is the simple variance of a stratified simple random sampling design. We have the second population with different clusters, and we need to estimate the second population, the total of the second population for a variable R. This is the indirect sampling process. When we observe a farm, we observe all the units, all the households related to that farm. This household, for instance, is could be observed even from that farm. From observing the second farm. For building a based estimator, Lavalle proposes the well-known generalized Weiss-Scher method that with the transformation of the target variable in a zeta variables, we can obtain the estimate of the total of the population B, considering the original weight for the population A. This is a very powerful transformation because the two designs are symmetric in this way. And the variance is the same variance considered the transformed variance of the. And so this is the problem. The problem is to minimize the total cost, bounding the variance of the estimates of both the variables of both populations. This is a multivariate, multi-domain problem. These are the variables of the first population. These are the variables of this of the second population, and we find the optimal inclusion probabilities. Because in the integrated survey framework, we define only the inclusion probabilities of the first population. But the problem as presented before is very theoretical, because we need to know the variables of interest for both populations and the links of, between the two populations. Now we consider 3 more concrete situations. The first situation, the links between the two populations are known in the design phase. We know which are the links. The second situation, the links are estimated during the design phase. The third situation, no links between the two populations are available, but auxiliary variables on the first population can provide useful information on the links. These are the context, the information, the situation. The first context, we are, this context is realistic in countries as the Nordic ones, having well-established register-based system. We have different population. We know all the links between those populations. The values of interest are unknown, but can be predicted using superpopulation models. In this superpopulation model, we have to determine only the predicted value for a model and the variance of this predicted value as sigma square. The more is more high is this value, the model uncertainty is higher. 5 minutes. 2. Using these, we can adopt our problem changes. We have the anticipated variance as target variable that can be decomposed in this way, where this is the expectation under the model, and the problem becomes this problem. This, in the second context, we don't know exactly the links. We can predict the links with some record linkage procedure, and the problems become this problem where the expectation must, for the second population, must consider the uncertainty on the links. But in this context, we have uncertainty on survey costs for each unit, because it depends on the uncertainty on the links. And so the problem becomes this problem. The third context is the most common in developing countries. And for instance, one might have a list of farms, but not a list of rural households. Or we can have a census of agriculture and not a list of farms. It can be, and we propose 3 different approaches for this problem. The first is a variable that can predict the link and construct a prediction of the zeta variable, assuming a uniformity in the links and defining a k-value explaining this relationship. The problem can be presented as the variance of the predicted values of the zeta variables, and this key value goes to in the denominator of the constraints. The second contest is the same, but we introduce an uncertainty on the prediction. And the third context is the more complex. The three options, the first is the most simply and the less costly, but is the less precise. The empirical results, we had a data set of Gaza province in Mozambique for households and farms. These are real data. We linked this real data, and in order to have a realistic setup for our simulation, we considered a problem with 4 domains and 2 variables. And so we have the problem with 8 target variables, multi-domain, multivariate problems. And these are the results. First, we consider a context 0, no control on the second population. And the other contexts were described here. The main results of the context 0, not considering explicitly the second population, the context 0 versus the context 1, allow that the estimates on the second population may be very imprecise. The integrated approach on the sampling allocation enables to count the precision of the estimates for both populations, however paying some loss in precision for the estimates of the first population. Context 1 versus context 2, the main result is that in presence of strong links, if we have good prediction of links, there is only a small increase in the sample size. This is, but as the links becomes weaker, the sample sizes increases significantly. And for the test okay, thank you. For the third contest, the maximization of links and certainty causes a significant increase in the sample size. The main consideration, the main conclusion, the integrated observation is essential to measure global phenomena which impact on different populations. Main advantage is cross-tabulation of the two populations, and it is necessary when we don't have the sampling frame for the second population. If it is not done, it's controlled, it is not performed in integrated approach, the variance for the second population can be very high, and we need to have good models for predicting variables and for predicting linkages for having, we need to have good models. Thank you for the attention.
Yeah, thank you, Pyro, and thanks to all for a distinguished speaker for the excellent presentation. And if you see, the topic coverage is totally different. 4 speakers for different topics, but constant was time. And due to, again, lack of time, we cannot take question, but our speakers will be available for the further discussion if you have. And follow on, actually, these papers, full papers will be available. At least the papers are available with me, actually, 3 papers, but it will be available on ICAS website as well. You can follow the paper. And with this, I thank the speaker again and the audience. We have got a good number of audience. It itself shows the importance of the topic presented in this session. With this, I thank all speakers and audience, and I like to close the session. Thank you all.
I thank the chairman, Dr. Hukum Chandra sir, for conducting this session. Now I invite you all for the lunch. The lunch will be served at 12:30 p.m. in front lawns. Thank you so much.